Okay, so this is the experimental setup required to verify the Charles law. If I remind you the Charles law, the law says the volume of a gas is proportional to the absolute temperature of the gas given that the gas is at constant pressure. Okay, then I'll be explaining the experimental setup. So you have a narrow glass tube with one end closed and containing a mercury index like this. So a dry air column is trapped inside this glass tube. Then you have this thermometer which is calibrated from 0 to 100 centigrades. Then this is scale. This is scale board. It is calibrated in millimeters, and the thermometer and the narrow glass tube is attached to this scale board using a few rubber bands. Then you have this stirrer, then a tall beaker of water. Then you have this tripod. On top of the tripod, we have to place a wire gauge. Then we can place this beaker on that wire gauge and complete the setup like this. And also you have this Bunsen burner. So this is the list of materials and apparatus required for the experiment. So according to Charles' law, the volume of a gas is proportional to its absolute temperature, given that the pressure of the gas is at constant pressure. So we can write that like this: the volume of the gas proportional to the absolute temperature. So this temperature should be in kelvins, not in centigrades. So to apply this equation, pressure should be constant. Then using a constant K, we can write this as an equation. So it is V equals K T. So we are applying this equation to the trapped air column. So there's trapped air inside this tube like this. Let's say the internal cross-sectional area of the glass tube is capital A, and the length of this trapped air column is simple L. Then we can write the volume of trapped air as L times capital A. So this V is L times capital A. So this should be equal to K T. Then I am going to subject simple L. So L equals K over A times T. So we have ended up with this equation. The reason to gain this equation is to draw a graph. So we are going to verify Charles' law using a graph. Before drawing the graph, we have to identify independent and dependent variables. So here the dependent variable is simple L. Independent variable is capital T. So L should be variable Y, T should be variable X. So what we are going to do is to change the temperature of water and give this a few temperature values, and depending on the temperatures, the length of this trapped air column changes. Then we can get a few coordinates, XY coordinates, and draw a graph. So the graph should be something like this. y-axis, symbol L, x-axis, capital T. So this capital T should be in kelvins, L can be in centimeters. According to this equation, this graph should be y equals mx. There cannot be an intercept. So the graph should be a line which goes through the origin. The graph should be something like this. So if we get the experimental data that matches with this graph, this combination is true. Likewise, this combination and the Charles law is verified. Then let's consider step by step how to continue this experiment. First, you have to attach the glass tube to the scale as shown here using rubber bands. And the close end of the glass tube should coincide with the zero of the scale. Then you have to attach the thermometer as well. The bulb of the thermometer should be closer to middle of the glass tube. So once the setup is complete like this, you have to note down the temperature reading and the length of this trapped air column. The length can be read using this scale. So those values are related to the room temperatures. So when applying Charles' law, the pressure must be constant. So how can we maintain a constant pressure inside the trapped air? If you can notice, the pressure of the trapped air is always the atmospheric pressure plus the hydrostatic pressure due to this mercury index. So regardless of the position of the mercury index, pressure inside the trapped air is atmospheric pressure plus hydrostatic pressure of the mercury index. It remains a constant. So the pressure of trapped air also should be constant. Okay, then we are going to heat up water inside the beaker. So while heating up this, you have to stir water. So it can maintain a uniform temperature all over water. Once the temperature of water is risen by about 10 centigrades, note down that reading, the temperature reading and the length of the trapped air column. When the Bunsen burner is on, it constantly provides heat to the water. So the length of trapped air column constantly increases. So we cannot get a certain value for the length of the trapped air. So you have to keep the length of trapped air for a while in order to get the temperature reading and the length measurement. So how can we do that? So we have to maintain the length of trapped air column to a certain level for a while. Now the temperature has risen to about 35 centigrades. So this reading keeps increasing. So now the reading is at, let's say, at 37. So once it has reached 37, you have to remove the Bunsen burner or switch off the Bunsen burner and let the system to cool down. So the length of trapped air that decreases and also the temperature reading decreases. Once it passes about the 35 mark, the temperature mark of the thermometer. Again, you have to switch on or place the Bunsen burner. Then again, the temperature increases. So we have to maintain the temperature reading somewhere here. Then we can assume that temperature remained at 35 centigrade. So once the mercury index is steady, you have to get the length measurement and the temperature at that moment. Likewise, at every 10 centigrade increase, you have to get about 6 pairs of readings for temperature and the length of trapped air column. Then you have to enter all those readings in a table like this. So this row has temperature readings in centigrades. This thermometer gives readings in centigrades. Okay. Let's say this is 25 and 35, 45, 55, 65 and 70. So let's say these are the temperature readings in centigrades. The sun exactly have to be at a gap of 10 centigrades. Okay. So it should be about 10 centigrades. So if you remember the Charles law, the temperature should be in Kelvin. So I have to convert these centigrade readings to Kelvin. So how can we convert it? Simply by adding 273. To be exact, it should be 273.15. We don't need that much accuracy, so we are just going to add 273 to each of these readings. So if we add 273 to 25, becomes 892. So the reading 273, 8, 308, 318, 328, 338, 348. Temperature readings in Kelvin is converted like this. So the length measurements have already taken. So then you have to fill this row with the related length measurements. Then you can get a graph. So this is length in centimeters. The x-axis is temperature, it should be in Kelvin. This is x variable. This should be the y variable. So you have pairs of readings for temperature and length. And you can mark those values. For the temperature and length, then there's this mark. And there can be mark like this, coordinate like this, and there are 6 coordinates. Then draw a base fitted line. And this base fitted line should go through the origin of the graph. Otherwise, the Boyle's law is not verified. It should go through the origin and it should be linear. So the graph should be something like this. Okay, now we know how to verify the Charles law. Then there are some special notes that we have to consider to increase the accuracy of the experimental results. One of the problems using mercury here is that the mercury tends to stick to the inner walls of the glass tube. So that can cause an error to the experimental results. We can minimize that error by taking the length measurements when temperature increases and when temperature decreases as well. So let's say at 50 centigrades, the length measurement of trapped air column is 25 centimeters. So this measurement is taken as temperature increases. So at 50 centigrades, we have to get a length measurement as the temperature decreases. Then that temperature measurement can be like 26 centimeters. So to minimize this error, we have to consider the length measurement at 50 centigrades as the mean of these two values. So it should be 50 plus 55 plus 26 divided by 2. So for all those temperature readings, you can consider a mean length measurement as the correct length measurement. Another issue can be that the spread of length measurements being small. We can prevent that by introducing a large volume of trapped air initially. So we have to increase the volume of the trapped air at room temperature. So at the length of trapped air at room temperature is the initial reading. We can do this by bending this glass tube like this. Of course, you have to use a lengthier glass tube. So you can use the glass tube like this, and this also helps saving up the space inside the container. So it can be like this. So we can place the marker index here. As you can see, now the initial trapped air volume is larger than here. So let's say the volume of this bent tube is V0. So it is the volume of tube below this level. Then simple level should be measured from this level. Then we can apply Charles' law to the trapped air here. So this is the Charles' law, V equals KT. Now the volume is the volume inside this straight part, the vertical part, that should be AL. And you have to add the volume of this bent tube. Let's say that volume is V0. Similarly, it should be equal to KT. Then I'm going to subject symbol L. So we subject it, becomes KT over A minus V0 over A. So this is why T is symbol X, and this term should be the gradient, and this is intercept. So if we arrange the experiment like this to get a good spread along the length measurements, the graph should be linear and containing a positive gradient and a negative intercept. So the graph should be something like this. So it should contain a negative intercept and a positive gradient, like this.